Now we are looking at Bayes decision theory. So if we are dealing with several classes, then the Bayes formula with several classes is that we have the posterior probability of X being from class Ci, which is equivalent to that thing here. This is basically the same thing that we saw just before, but for more than 2 classes. And the thing to look at is the evidence here, which is summing over all classes, the prior times the likelihood. So here we know that the probability is higher or is equal to 0, and it is in fact below 1 or at 1 at max, because the sum of all prior probabilities is equal to 1. And then we are choosing the class. We are making a decision based on the posterior probability. So we are assigning X to the class that is having the highest probability according to the posterior. So we are looking at the argmax. So those who miss that, argmax is basically the index or the value for which what we are looking on the right side is maximum. So here argmax give us, so we are looking from key equal to 1 to k. So it will give us the class for which ck given x is maximum. So this gives us like the index of the maximum value of what we are looking for compared to a max, which gives us simply the maximum value. So here we obtain as a result the class which is maximizing the posterior probability. One thing, however, is that not all decisions have the same impact. For example, with the credit risk evaluation example, lending money to a high-risk client is not the same thing that lending money to a low-risk client. So the possible outcome of giving some credit to someone that is not able to pay back can be much higher for a credit company that denying the credit access for someone with a lower risk. Because we will lose a client for a low-risk client. So yes, there are some profit not made here, but the consequences are likely to be much less than giving money to a client that is at high risk. So the decision the decisions should be done accordingly. Same kind of situation with medical diagnosis. Getting into a false positive, so detecting illness into someone which does not have the illness is not a good thing, it's a bad thing, but the impacts are likely to be much less than false negative. So missing the fact that someone has an illness, think about, for example, someone who has cancer and the test is negative, so it means that we aren't detecting the cancer. The impacts can be huge for that person if we are not treating that person quickly. But if on the opposite, we are detecting a cancer to someone that has not a cancer, well, it's not fun, but the impact are likely to be much less. And we are probably able to detect again that it was a wrong detection. So in that case, we may adjust the things. We may want not everything to be equivalent. We may say that, yeah, it's much more costful to make decision A than decision B if in both cases we are in mistake. So we are defining a quantity with a loss function. This loss function here, which is the big L, the big calligraphic L, takes into account the action. So the action is alpha I. So this is the decision we are making, while the real class, the real thing is in Cj here. So we are looking at the fact that we are making a wrong, maybe a decision alpha I that may be different from the real class Cj. And from that, we are computing the expected risk. So let's say that we are making an action alpha. So that action alpha corresponds to the sum over all classes. And we are looking at the loss of making decision alpha given that CK is the real label times the posterior probability. This is where we get back the posterior probability and say, okay, the posterior probability is the probability that X is coming from class CK. So we are looking at the possible outcomes, the possible probabilities, and we are multiplying this with the loss, and that gives us the risk. So that risk is somehow the loss weighted by the posterior probability given by our model. And in such case, we will take the action that is minimizing the risk. So alpha star here is basically the alpha for which the expected risk is minimum. So modifying the loss function changes the risk. So if we are using different loss functions, possibly not the same action will be picked in a given situation. So we can then modify the cost associated to false negative relatively to the cost of false positive, like in the examples I just explained you a few minutes ago. So in the case of two classes, we can get with what we call a confusion matrix. Basically, the confusion matrix is representing the loss function. And in that specific case, we just say, okay, when we are making the right decision, we just assign to class 0 when it is from class 0. The loss is 0. Likewise, if we are assigning to class 1 here, while it is really class 1, the loss is also 0. So on the diagonal, the cost is 0. That's fine because these are the cases where when we are making the right decision, the correct decision. And in the other cases, we are looking at first, let's say that we are making as decision positive, so alpha 1, while the real thing was negative, was C0. Then we have the lambda of false positive. This is the cost of making a false positive decision. Conversely, we have the case that we are making as decision 0 while it is 1. So this is the cost of a false negative. So basically, we can say that this is equivalent in basic cases, but for more fancy cases, we can use different values for this lambda fp, lambda fn. So with k classes, this is just a generalization of that matrix. We basically say, okay, on the diagonal, the cost is 0 because everything is fine. And elsewhere, we have the cost of, for example, here, it's just the fact that we are picking alpha 1. So we are making decision for associated to class 1, while it is from class 0. So this is the fact that we are mistaking a sample as class 1 while it is from class 0, and so on for all the other possibilities. A simple version of that will be the 0,1 loss function. The 0,1 loss function is basically to get back to our original formulation where everything is equal, all types of errors are equivalent. So in such case, we just say, okay, we get a confusion matrix where on the diagonal it is zeros and everywhere else it is 1. So the cost is the same for all kinds of mistakes. And so simplifying this to that function, which is just saying that the loss is equal to 0 when I is equal to j. So basically when the decision is for the right class. And the loss is 1 for all other cases when we are making mistakes. And so the corresponding risk here is, if we take the expected risk formula, we are summing over all classes. So the decision, and we are looking at the loss associated to assigning to class alpha I to class I, given that it is from class K, times the posterior here, which is given by our model according to class X. Given that we have all ones except for the case when I is equal to j, or in the summation when k is equal to 1, we are summing all the posterior probabilities where this thing is equal to 1, except for the case when k is equal to I. When k is equal to I, we are in the case of 0 loss here. So we are not counting it, we are counting everything else. So, and then we are summing the posterior probability for all classes except the right class for that data X. This gives us basically, given that the sum for all posterior for PC k given X from 1 to k is equal to 1. So summing all this from I equal to 1, k equal to 1 to k give us 1. Then we just say, okay, let's use the formulation where we say this is equivalent to 1 minus the posterior probability of the right class of the ground truth class. So the class that is the real class from that sample X. This is the risk, the expected risk for the 0, 1 loss function. And then the optimal decision is basically to choose as action the one that is corresponding to the class which has the maximum posterior probability. So we have this thing here, which is the posterior. So we are using as decision the class for which the posterior is maximum. So we are falling back on the original result before talking about varying cost. But we can use different costs, and then we are not using this. And we can even go further by saying that in many applications, a bad classification can have a huge impact. So in some cases, we may want to get what we call a reject option. That reject option is that we have some doubts on that data. We are not sure about which class this data is coming from. So we can also decide to reject. So we have an action that is rejection, and we assume that the cost of rejection, there is a cost, but it is less than making a mistake. So if we go back to the 0, 1 loss function with reject, it is something like this. So we say that if we are making the right decision, the cost is 0. If we are making a decision and it is the wrong one, the cost is 1. If we are making a reject decision, so if you are making use of the reject option, the cost is lambda. And this lambda is assumed to be between 0 and 1. So because if it is higher than 1, we don't need to reject, we will just make decisions. And between 0 and 1, it means that the reject option costs less than making a mistake. In that case, the expected risk is something like this. So we just look at the risk for a decision, any decisions among the classes. This is the same thing than before. We just get this equivalent to 1 minus PCI given X, where, so this is the risk of assigning to class I, assuming that this is our risk for assigning to class I. And then we have the risk for rejecting, which is equivalent basically to lambda, because we are summing over all the k's. So basically the sum of ck given x from 1 to k is equal to 1. So it's always times lambda. So basically it boils down to lambda. So this gives us, I would say, the risk for the two cases of classifying or rejecting. Then optimal decisions with reject option is equivalent to this thing. So it's basically the same formula than before, except that we go up to an alpha of k plus 1, not just alpha k. So we add in the range of possible values the reject option, and we are looking at the risk for each of these cases. So the decision that will be made here is that we will reject. So we will take as decision rejection if the probability for all classes, all possible decisions except reject, if these probabilities, the associated posterior is less than 1 minus lambda. So if all posterior are less than 1 minus lambda, it's better to reject. Otherwise, we will make a decision by picking up the class that has the highest posterior probability. And then we get into a new confusion matrix that is an extension of the two first that we saw. So we have k classes, but we also have a reject option. So this is no more a square matrix. This is rather a matrix of k plus 1 columns because we are adding these columns here versus k lines. So all these things is the same that we had before for k classes plus 1 column, which is the column of the rejection cost, basically. And so from that, we can build discriminant functions for classification. So we have here a function that is picking up the class for which we have HIXT maximum. So what is HIXT? It's basically our output from our model. And then we are assigning a sample XT to the class that is corresponding to the maximum HI. So in the Bayesian case, in general, we just say that HI is equal to minus the risk, because somehow the risk is higher the risk, lower the chances, or maybe it's not what we would try to minimize the risk. So in terms of discrimination, we try to maximize the H. So in terms of converting from a min to a max, we are adding the minus sign over the risk. And as for the rest, it is HI is equal to minus the risk. And so with Bayesian, if we have a Bayesian case with 0, 1 loss function, we can just state that HI is equivalent to the posterior of that class. So we'd say that we have a function HI, and that function corresponds to the posterior probability of getting, given the sample X, it is getting from the class CI. And so we can then convert, so this PCI given X is equivalent to PCI P, oh, sorry. So P X given CI, so we have the prior times the likelihood divided by the evidence. But given that this evidence here is the same for all classes, it doesn't change, we can just ignore it. And we just have to pick the top of the Bayes rules, which is that thing. So basically we will say, we will assign then we will use as function HI the likelihood times the prior, ignoring the evidence because it is the same for all classes. And from that, we just apply the HI into the equation and we will pick up the right class. From this, we can define what we call decision regions. So we could say that given our input space, we can partition it in k regions. So each of these regions correspond to the region where the HI is maximum. So this formulation here is just stating that let's get in the space of X, so the input space that we have. We will assign to Ri the space where HI of X correspond to is maximum. This is equivalent to the maximum H that we have over all classes. So basically, we just kind of draw the space, the region where that class has the maximum HI. And this for all classes from class 1 to K. And these decision regions are separated by decision boundaries. So we have these boundaries that are kind of splitting the regions that are already defining the frontiers between these regions. And so in two classes, we see that we have what we call a dichotomizer. So dichotomizer is basically to cut the space in two. In two classes or more, we have what I call a plurichotomizer, which is a neologism. This is not a real word, but somehow it is an extension of this idea of dichotomizing into classes. So with a reject option, in fact, we have this thing here. We could just say that the dots are real points, and then we have the dashed lines which correspond to the region where we have, I would say, probability higher than 0.5 because we are using a lambda of 0.5, which is the cost. The cost of rejection is 0.5, the cost of a bad decision is 1. So then we could say, okay, all this region here correspond to class 1. This is the region of the red dots. Likewise, we have that region here. It's corresponding to the green dots, class 2. So all this region is the part of the space where the posterior PC2 given x, so the posterior for class 2 is higher than 0.5. And likewise for the class 3 here. And this is the region, so where everything is from class 3, the posterior is 0.5 or higher for class 3 here. And in between, you know, like this region here, that region there, that region there, this is the region of rejection. So this is the region where the posterior of all 3 classes is below 0.5, given that we use a lambda, a cost of rejection of 0.5. This is where we will reject. Basically, if we get a sample there, we have too low certainty about that regions to make a decision.